Greetings and welcome to the Introduction to Astronomy. In this week's episode of New Discoveries in Astronomy, we will talk about how we are reading the atmospheres of distant worlds. So let's get started. How can we know what a planet is made of when we can't see it directly? Most exoplanets are far too distant to observe in detail. We don't see their surfaces, we don't sample their atmospheres, and yet astronomers are now measuring the chemistry of these worlds, not by imaging, but by studying how they affect starlight. When a planet passes in front of its host star, it blocks a small fraction of the star's light. This is called a transit. But something subtle also happens. A tiny portion of that starlight passes through the planet's atmosphere before reaching us. And that light carries information, not about the surface, but about the gases surrounding the planet. As that light passes through the atmosphere, different molecules absorb different wavelengths. If we spread that light out by wavelength into a spectrum, water vapor absorbs some wavelengths, carbon dioxide absorbs others. Methane leaves its own distinct pattern. What reaches us is no longer the original starlight, but a modified spectrum, a pattern of missing wavelengths, like a fingerprint. This is where measurement becomes inference. Just like other areas of astronomy, we are not observing the object directly. We're interpreting a pattern in the signal. Astronomers don't see the molecules directly. Instead, they compare the observed spectrum to known molecular signatures. If certain wavelengths are missing, and those missing wavelengths match specific molecules, then those molecules must be present in the atmosphere. By analyzing how strong these absorption features are, scientists can estimate how much of each gas is present, and studying how those features change, they can infer temperature and atmospheric structure, all from subtle changes in light. Using the James Webb Space Telescope, astronomers studied the atmosphere of TOI 5205b as it passed in front of its star. By analyzing how the starlight changed, they were able to measure the chemical composition of the atmosphere. But the result was unexpected. The atmosphere contained fewer heavy elements than predicted, even less than the star it orbits. That's the key result. It challenges our current understanding of how giant planets form. And that has broader implications. It suggests that the processes that build planetary systems may be more diverse than our models predict. Not by observing these worlds directly, but by analyzing the light they filter. We often imagine exploration as something direct, seeing, landing, touching. But for distant worlds, we rely on something more subtle. A small fraction of starlight, filtered through an atmosphere, can reveal the composition of an entire planet. Not because we observe it directly, but because we've learned how to interpret the signals it leaves behind. So that concludes our discussion on reading the atmospheres of distant worlds. We'll be back again next week for another new discovery in astronomy. So until then, have a great day, everyone, and I will see you in class.